Ah, okay. So as I announced, so we take the midterm exam on Thursday, and then during the regular class time, right? And then so actually the exam will cover the chapter one, chapter two, and then system very low part. Okay, as I announced, so it means the today's class will be also included in the midterm exam, right? So actually, so I will cover until the chapter two in the today's class, and then I will end the class. So the weather is so great because it's the midterm exam period, right? 항상 시험 기간이 제일 날씨가 좋죠. 한국이 이제 봄하고 이제 in Korea the fall and then spring is the kind of best uh, best season in here, but actually during the best season, so we need to take the exam. Okay, so in the previous class we learned about the multiplexer. So we are learning about some basic combinational blocks, and then multiplexers. Multiplexers are also very important combinational blocks. So it means we frequently use multiplexers in the digital system, right? So it is because the so you need to remember you need to understand the definition of a multiplexer. Okay, so multiplexer has multiple inputs, and then based on the selection signal, then we can select the one of multiple inputs. Okay, so output is just connected to the one of multiple inputs. So that is the definition of a multiplexer, right? So we learned about the 2-to-1 multiplexer. Okay, so the first number represents the number of inputs, and then actually the one. Actually, in the multiplexer we have only one output, but we just represent the multiplexer as the n-to-1 multiplexer. N means the the number of inputs, and then one is also number of output, right? So this is the 2-to-1 multiplexer, and then we learned that we can implement a 2-to-1 multiplexer using SOP form, like the AND gate followed by OR gate, and we can also implement a multiplexer using tri-stage gate, right? Like this. Okay, then we can also consider the 4-to-1 multiplexer. So by the definition, the 4-to-1 multiplexer means the input has, but this multiplexer has 4 input ports and then 1 output port. So this is, and then you can find the symbol of 4-to-1 multiplexer, right? So this is the selection signal, but we need to select from 4 input signals. So it means the selection signal, the bit width of the selection signal needs to be 2, right? So we need to classify some inputs. So we need to decode the input signals. So the selection signal needs to have 4 different values, obviously, right? So like 0, 0, 0, 1, 1, 0, 1, 1. And then based on the selection signal, we can select one of inputs in the multiplexer, right? So this symbol represents that if the selection signal is 0, 0, then D0 is selected, and then the Y is connected to D0. Okay, so this is the multiplexer, 4-to-1 multiplexer. And then we can implement this 4-to-1 multiplexer using 2-to-1 multiplexers hierarchically. Okay, so this is also an example of hierarchical design. Okay, we learned about the 3 Ys in the first one, the second class, right? So this is the so this is the example. So we can hierarchically organize 2-to-1 multiplexer to implement 4-to-1 multiplexer. Okay. So firstly, we can select the D0 or D1 using the S0. Okay. And then D2 and then D3 using also S0. It's the same signal. This is also S0. And then using the S1, then we can also select the output of this multiplexer or the output of this multiplexer, okay, using the S1. So actually this is the same. So this is the same circuit, okay. So if you see this symbol, then actually if the S1 is 1, then we can select the D2 or D3, right? So like this. So we can select this path in the this hierarchical multiplexer, right? So it's this is the equivalent design. But if you can understand so this is equivalent design. So if you can understand the definition, just the definition of a multiplexer, then I believe you can easily understand the meaning of this hierarchical design, right? So you can just test the values of S0 or S1, okay? Okay, so this is also another circuit design of a 4-to-1 multiplexer. So we it's like the the 2-to-1 multiplexer implemented by SOP form. So we can also implement the 4-to-1 multiplexer using SOP form, right? But in the SOP form, so you can just understand that. So you can find the two inputs of this three input of AND gate, and then the S0 and S1, or the S0 bar or S1 bar are connected to this three input AND gate. Okay, so if these two ports are all ones, then this AND gate is activated, right? So A and 1 equal A. So which means that if the one of input of AND gate is 1, right? Then the A is just connected to the output. So it means that the A just passes this gate. So you can understand the SOP form of the multiplexer design like this. So using the S1 and S0, the referrals of S0 and S1, then we can activate. So we can activate this one of these AND gate. And then we can just work the output of AND gate, okay? AND gate. So this is the SOP form implementation of a multiplexer. Also, we can implement this 4-to-1 multiplexer using tri-state gate. Like it's the same. So we can just enable the one of these 4 tri-state gates, right? So using the S0 or S1 signal, we can just enable one of these 4 tri-state gates. So we can select the one of inputs, and then this selected input is connected to the output. So this is the tri-state gate implementation of the multiplexer. Okay. Okay, so and then I will discuss about some properties of multiplexer. So this is very interesting property. So you can find the truth table here, and then it's just some actually this is A bar A, A bar B, A bar and B. Okay, so this is the truth table of A bar and B, right? Because the Y is 1, and if the A is 0 and B is 1, right? And then actually using a multiplexer, we can implement this truth table. Okay, how? So you can find that A and B are connected to the selection signal, so the selection port of the multiplexer, and then the inputs of this multiplexer is connected to ground or VDD. So ground, it means the 0, right? Because it's a ground, right? The 0 voltage. And this port is connected to the 1. So what does that mean? So and then the A is S1 and B is connected to the S0. So which means this is the port 01. Okay. So if A is 0, right? Because the A is 0, A is connected to the S1, and B is 1, right? Then Y becomes 1, right? Because the Y is connected to 1. Okay. So this port, this port, this port is just connected to the high voltage, the VDD. So it means that if this port is selected by this multiplexer, then Y becomes 1. But if A is 0 and B is 1. So we can observe that using a multiplexer, we can implement this Boolean equation. Okay, A bar and B. Okay, so in this circuit, actually, so this port, input port represent minterms. Input port represent the minterm, and then actually we can input port to represent some literals, and then we can select the midterm right here. Okay, so which means that this midterm will make sorry, this midterm will make output 1, right? So and then this term is just connected to 1, so only this input is selected if A is 0 and B is 1. Okay, it's the same meaning. Okay, so it means we can implement any Boolean equation, actually, any Boolean equations using multiplexer. So it means that we can say that we can use multiplexer. We can use multiplexer as a lookup table. Okay. So lookup table means that based on the certain input, then we can select a certain output. Okay, a defined output. That is the meaning of a lookup table. So we can implement lookup table using a multiplexer. So it means that we can implement any Boolean equations using a multiplexer. Okay. So this is actually very important. It's important. So it means actually in FPGA. So so it's a kind of some advanced level of the discourse. But in FPGA, the FPGA has many lookup tables, and so actually we can implement any Boolean logic using lookup table of this in FPGA. Okay, so actually we can use the multiplexer. So this is very important. Okay. So it means so we can implement the basic logic gate using a multiplexer. So if we use the 2-to-1 multiplexer, then we can implement the 2 input basic logic gate. Okay. So this is an example. So if y equal AB, so this is the AND gate, right? So you know, for this multiplexer, the only one port. So if the A is 1 and B is 1, then this will be selected, but it is only connected to the VDD, okay, high voltage. And then other ports are connected to ground, so 0. So it represents the Y equal AB and the gate. So with the same way, so so this is the OR gate, right? So if the AB is 0, 1, 1, 0, and 1, 1, then Y will be 1. And then if the AB is all AB are all zeros, then Y is 0. This is OR gate, and then this is exclusive OR gate. So actually, using 2 to 1 multiplex, 4 to 1 multiplexer, we can implement any two input logic gate, two input basic logic gate. Okay. So using a two power of n input multiplexer, we can implement the any n input logic function. Okay. So this is very important and critical and interesting property of a multiplexer. So this can be included in the exam problem. Okay? So this is very interesting. So we can implement we can implement any logic using multiplexer, right? And then also, so we can simplify the multiplexer design like this. So if you see the AB function, so it's a A and B, so this is the logic function, then you can find that if the A is 1, then Y is equivalent to B. So this is actually the property of AND gate, right? So the if the Y equal A, B, and then if A equal 1, so it means that Y equal 1 and B, so it's actually B. So this is the truth table of this AND gate A and B, but we can rewrite this truth table like this. So if the A is 0, then Y is obviously 0, right? But if the A is 1, then Y is equivalent to B, right? Right, because it's a 0, 1. So actually, if the A is 1, then the B is equivalent. The Y is equivalent to B, right? So we can simplify this truth table like this, and then which means we can implement this AND gate using 2 to 1 multiplexer like this. So what does that mean? If the A is 0, then 0 is selected for Y. And then if A is 1, okay, then B is selected. So Y equal B. So this is equivalent to Y equal A, B. A and B, right? So we can simplify. So basically we can implement any logic function using this multiplexer, but we can also simplify this table like this. Then we can just implement we can simplify. Okay, actually, we can simplify the implementation of the multiplexer like this. Okay, it's also interesting. So we can simplify. We can use the smaller circuit to implement this logic. Okay. Okay, so this is the multiplexer, and then now, so we will learn about the decoder. So decoder has n input and then 2 to the power of n output. right? And then you can find the truth table of decoder. So if you just see the truth table of the decoder, then you can understand the behavior of decoder. Also the meaning, the some definition of the decoder. Okay, so what is this? So if the A, so this is the 2 to 4 decoder, so which means that the first number represents the number of inputs, right? And then the second number represents the number of output ports, right? So it means that it's a 2 to 4. So actually, in a normal decoder, a normal decoder has the n input and then 2 to the power of n output. Okay, so this is the example of 2 to 4 decoder, right? So, and then this is the some truth table. So if the A is 0, 0, okay, so it means it's a 0, then we just activate the first bit, the Y0, to deactivate the Y0. And then if the A is the 0, 1, we just activate the Y1. So you can understand. So if the it means the Y, so this is the A. So if the A has the some number, right? Then we just activate the Y x equal 1 and other Y becomes 0. So this is the definition. So just the behavior of a decoder. So you can find that if the Y has the some value like X, then we just activate the Y, the X bit of output port. Okay, it just activate the one of output port. Okay, it just make one of output ports 1 based on the input value. Okay, this is the definition. That's just definition. So it's a definition. So you need to memorize. You need to memorize the definition, right? So and then actually this decoder is also frequently used in the digital system. So actually decoders are used in the memory, okay? Like DRAM or SRAM and some other memory components. Okay. So I will actually we will learn about the memory in the later. Okay. So this is the implementation of the decoder. Okay, and then this is the SOP form. So you can find that the A0 here, so we use the literals of A, right? So you can, so this is the A1, and this is the A1 bar, and then this is A0, and this is the A0 bar. And then it's just simple. So in order to activate the Y0, in order to make the Y0 1, then we need to use this line and this line, right? So which means that the A1, A0. Okay, and then this is the AND gate. So Y equal A1 bar and A0 bar. So then Y0 will become 1, right? So Y1 is the same. So Y1 is the A0 and A1 bar. So so A1 bar is here, then A0 is here. Just connect it to the AND gate, right? So this is the SOP form of the decoder. So okay. Also, if we just use the OR gate for the output of the output port of the decoder, and we can also make the SOP form. Okay. This is because in the implementation, you can find that So these are actually AND gate for the records of input ports, right?
Decoders are always one hot, or there can be multiple Ys with the same output.
The multiple same output, right? So you know, so it's a one hot code, right? As you said. So multiple output, like the y3. So if the y0 is 1, then y1 has the 0, y2 has the 0, y3 has the 0. Right. The multiple outputs will have the same 0 values, right?
Can Y0 and, for example, Y3 have be 1 at the same time?
So so you mean, so can you say it again?
Can Y0
Uh-huh.
be 1 and at the same time Y3 can be 1?
It's not possible. It's not possible. So because this is one hard code, only one output can have 1. Okay. So in the decoder, so actually the the multiple output ports cannot have some ones. Okay. Only one output. Only one output can have value 1. Okay. Understand? So this is the actually this is for the one hot encoding. So which means that actually the only one output signal has the value 1. Okay. So this is just the rule. So as you can see, so if you see this decoder implementation, you can find that the vectors of input signal are connected to the AND gate, right? And then, so, you know, this output, so this is the AND gate, and then, so, which means if we just connect the output of AND gate, if we just connect the some output of this AND gate, so which means that this is the some outputs of decoder using OR gate. So it looks like the AND gate, and followed by OR gate. So this is the SOP form. Okay, so it means using decoders, we can also represent SOP form of the Boolean equation, right? Because actually decoder includes this part, right? The AND gate, and then if we just use the additional OR gate connected to the some output signals of decoder, then we can implement the SOP form. Right. So which means using a decoder, we can also implement a logic function of any Boolean equations. Okay, because we can just connect the min terms of the input, right? So in this example, so this is the AB, right? So A is connected here and then B is connected here. And then each line, each output of this decoder represent the AB or AB bar, A bar B, and then A bar B bar, like the 0, 0, 0, 1, 1, 0, 1, 1. So this is the A, B. Okay, so we just know, so each output represents the min term of this AB inputs, and then if we just select a certain min terms to generate the output, then we can generate the SOP form. Okay. So in this example, we just select this port and this port, right? And then we OR the port 11 and then port 00. It represents the Y equal AB plus, because this is OR, and A bar, B bar, right? So the A bar, B bar is here, from here, then A is from here. So this is the exclusive OR gate, exclusive door gate, right? So we can implement the any Boolean logic using decoder also. Okay. So actually in the combinational block, we just learned about the multiplexer, and then we also learned about the decoder. Okay. So these are frequently used combinational blocks. Also, we learned that using multiplexers or decoders, we can implement any Boolean equation. Okay. Okay, now so let's okay. 네. 네 개로 해도 되고 아무거나 해도 됩니다. So this question is that among these four outputs, so can we select some three outputs or two outputs or one outputs? So actually, we can select any number of outputs, right? So for example, if the A, B, and then Y, 0, 0, 0, 1, 1, 0, 1, 1, and then if this is 1, 1, 1, 0, so you know, so this is AND gate, right? Then, so you know, so we can find the three midterms in this truth table. Then we can just select this port, this output, not this output, because 1, 1 is 0, so it's here. We can just select this output, and this output, and then connect the OR gate, three input OR gate, then we can implement this truth table. It's possible. So we can also select any numbers of outputs, okay, to implement the some logic function. Okay, so this is the example. If there are three midterms, we select the three outputs of decoder. Okay. Okay, good question. Okay, now let's learn about the timing of combinational logic. Okay, so when we learned about some components of a combinational module, so we learned that this module looks like this. So and then this module includes the input port, right? And then output port, and then also this module has the functional specification, like the Boolean equation. So until now, so we learned about how to implement the Boolean equation or functional specification using combinational logic, like F. And actually, we learned that each module also includes the timing specification. Okay, so it means that actually the output is not immediately output signals cannot immediately reflect change of input. It is because it's real hardware. Okay, so I mentioned that. So we are in the real world, we need to consider time. So the circuit, every circuit has delay, right? So it means that even though the input is changed, the output value will be changed after some time. That is called delay of a circuit, right? Actually, when we define a module, then we also need to define timing specification as well as functional specification. So we need to define timing specification. It means the delay of this circuit. Okay. So until this point, we just learned about the functional specification of a combinational block. But now we will learn about the timing specification, like delay. Okay. So you can understand like this. So y, the output is the function of inputs like A, but in delta t, delay. Okay. So in mathematics or some software, so we just understand a function like this. So it means that if the input is changed, the input value is changed, then output just immediately reflect the changes of in input signals. But actually in the real hardware, in the real world, then actually in delta t. Okay, so output is changed after a delay. Okay, so then actually in every module, every hardware module also includes this timing specification. Okay, so let's learn about the timing. So as I mentioned, every electric circuit exhibits delay. Okay, so this is the example. So this is the buffer, right? It's a buffer. So this is a symbol of buffer. Okay, and then the A is changing. A is changing like this. So A is changing from 0 to 1. Okay, looks like this. But as I mentioned, the Y cannot change it immediately. After some delay, like this delta t, then you can find that output is changed. So even though the input is changed at this time, the output value reflect the change of input at this time. So this time gap is called the delay of the circuit. Okay, and then actually when we define this module, then we also need to define this delay of the circuit. So it's called timing specification. Okay, so this is the definition of a delay. So delay means that the time between input change and output change. Okay, so this time gap is the delay of the circuit. And then we can define two different kinds of delay. So it's called a propagation delay and contamination delay. And then you can just understand that a propagation delay is the maximum delay. And then contamination delay is the minimum delay. Why there are two different kinds of delay need to be why two different kinds of delay need to be defined in the circuit. So this this example just to show the example of delay. So you can understand, oh, if the input is changed, then output can be changed. So okay, so that can be possible. So this is the hardware. But I also mentioned that, oh, we need to define two different kinds of delay, like propagation delay and contamination delay. Also, you can find that, or you can understand that propagation delay is the maximum delay. So it's the longest delay. And then contamination delay is the minimum delay. And it means the shortest delay. Okay. So the propagation delay is represented using the T underbar TD. Okay. Then so this is the it represents the propagation delay, and then contamination delay is the CD. So this is the T underbar CD. Okay, it's a minimum delay from input to output. Then why? Why? So it is because so this is the buffer. So and then I also mentioned that. So actually we need to implement this logic using the pool of logic. Then we can implement the pool of logic using the PMOS transistor, and then we can also implement it requires the pull down logic, and then this is the NMOS transistor. Okay. This is why. So we learned that actually we need to use the CMOS transistors, right? It means that the CMOS transistors include PMOS transistors and NMOS transistors, right? And then we can implement the pull-up logic using PMOS transistors, and then pull-down logic using the NMOS transistor. And then the property. Actually, the properties of PMOS transistors and the properties of NMOS transistors are different. Okay, so for the rising, so from 0 to 1, this is called the rising of the circuit. Actually, the rising is the rising signal is determined by pull-up logic, and then the falling signal, the signal value changes from 1 to 0. So this signal is determined by pull down logic. And then, obviously the properties of NMOS transistors and the PMOS transistors are different. So it means that the delays can be also different. So because of these the different characteristics or different properties, then we can define different delays. Okay, but we can just define the minimum delay and then maximum delay. So it means that actually between the TCD and then TPD, the output value Y is determined. So we can get, so if we just define the minimum delay and maximum delay, so it means that between this contamination and then propagation delay, then output value is determined. Okay, we can guarantee. Okay, so the delay. So as I mentioned, the delay. So okay, we need to implement. We need to implement basic logic gates using CMOS transistors and the electric circuit, and then because of capacitance and resistance in a circuit, then we can observe delay. Okay, delay is actually caused by capacitance and then resistance in a circuit. Okay, and then why TPD and then TCD may be different. Okay, so as I mentioned, different rising and then falling timing. So as I mentioned, the rising time is determined by from pull-up logic, and then falling delay. The falling time is also determined by pull-down logic. Okay, so it's a different. And then if we implement very complex circuit, then this circuit may have multiple inputs and then multiple outputs. Okay, so and then these multiple inputs and the multiple outputs may cause the difference in the propagation delay and contamination delay. Okay, so this is the some physical issues like the temperature, then process variation, and then voltage variation. It's called the PVT variation. So actually, this is the physical issues. So it means that we can make the transistors. So we can make CMOS transistors or so we can make this NMOS transistors or PMOS transistors, but the properties of these transistors are influenced by temperature and then process variation, like the processing error, and voltage level, so voltage variation. So because of these physical issues, then the delays can be changed. Okay, but you can understand that these are some physical issues. Okay. Okay. Then we can define propagation delay and contamination delay of this basic logic gate. Okay, like here and here. Also, we can define the propagation delay and contamination delay of this logic gate or gate. Okay, and we can also implement the logic using by combining multiple basic logic gate, right? Like this example. So I mentioned, so for the AND gate, so in this example, for the AND gate, we can define T, PD, propagation delay of AND. So we can define T, CD, a contamination delay of AND, right? And then for the OR gate, we can also define the TPD on the bar or the propagation delay of OR gate, and then we can define contamination delay OR gate. And then in this circuit, we can combine AND gates and OR gates to implement this circuit, right? So we can also calculate the propagation delay from input A, B, C, D to output Y. And we can also calculate the contamination delay of this circuit based on this information. Right? How? So actually, until the output Y, we can observe that if the signal starts from input A, and this signal will need to pass through this AND gate, this OR gate, and this AND gate. So it means that from input A to Y, we can find three basic logic gates, right? Two AND gates, and then one OR gate. So B is the same. Okay. But if the signal starts from B, this signal just has to this AND gate. So one AND gate, right? And then each logic gate exhibit its own delays. Then how can we calculate delays of this circuit. So simply we can add delays of basic logic gate, right? It's simple, right? Each logic gate exhibit delay information. Each logic gate includes delay information, and then for this logic, so and then we can build this complex logic by combining multiple logic gates, and then in order to calculate the delay of this logic, then we can just add it. We can just add delays of basic logic gate. Okay, then based on this information, we can calculate the propagation delay and contamination delay of this circuit. How? And then actually we can easily figure out that this path, the delay of this path is the longest delay, right? Because from input signal A to the output signal Y, we need to go through AND gate, OR gate, and then another AND gate. Okay, this path will exhibit the longest delay. So the propagation delay of this circuit will be the propagation delay of this path, right? Because it goes through the 3 gates. Okay, so we can calculate the propagation delay of this circuit like this. So this path, okay, from A to Y or from B to Y. So we can just add the propagation delay of the AND gate, and then there are 2 AND gates here, so we just double this propagation delay plus propagation delay of the OR gate. So it will become the propagation delay, the maximum delay of this circuit. Understand? Right? So because this is the maximum delay, the longest path. Now what is the shortest path? So actually from D to Y. Okay, this is shortest path. But in order to calculate the contamination delay, then we need to use the contamination delay of this AND gate. Right, this is the shortest path, shortest delay. Okay, so this is the TCD on the one hand. So, as I mentioned, each gate has propagation delay and contamination delay. Okay, and then we can combine. We can build complex logic by combining multiple gates. Right? In this case, we can just accumulate. We can just add the delays of all gates, okay, in the path. Okay, that's how we can compute. We can calculate the delay of the complex logic. But you need to remember that when we calculate the propagation delay, like the longest delay, then we need to use the propagation delay, obviously, propagation delay of the each gate. And then if we just calculate the shortest delay, then we need to use the contamination delay of each gate, right? Okay, this is very important. Okay, so if you can understand this, then it's okay. Then this is some additional information. So then I will define. So we will learn about some glitch. So glitches. So glitch means that the signal values are instantaneously changing. Okay, right? So actually, this change is not a permanent change. So it means that this is not a final value, but because of some different paths or some different packets or some different logic gate, then we can observe glitch. So this is some temporary changes in a signal. So we can observe the glitch like this. So it means that so it's the constant one, but we can find the some. So change the value is changed to 0, and then after some time, and then in a short time, then the value is also recovered to 1. So you can find some different kind of glitch like this. So it is 0, but like 1, and then it is 0. So as I mentioned, this glitch is not a final value. Okay, this is the some instant changes. So instant changes in signals, signal value. Okay, let's see the example. So this is the example. So A, oh, I not used. Okay, so A is 0, and then C is 1, and then B false. Okay, so which means that B was 1, but it changed to 0. Not use the sorry. So what's the final value for this circuit? Okay, if the A is 0, B is 1, and then C is 1, what is the Y? Y of the so it will be 1, and then no, this is 1, 0, 0, but it's Y is 1, right? Okay, so and then if the B false, so it means that A is 0, then B becomes 0, and then C is 1. Then what is the Y? Y is still 1, right? Is it because so this is 0, but it becomes 1, so it becomes 1. Okay, and then it is 0, so it becomes 1. So actually, if we just understand, if we just analyze the circuit in this manner, so it means if we do not consider delays of this circuit, then actually the output is the same. So if the A is 0 and B is 1 and C is 1, then output Y is 1, right? And then if the A is 0 and then B is 0 and then C is 1, then output Y is still 1. Okay? So even though the B is changed, B is changed from 1 to 0, output is the same. So which means that we can expect, oh, this is Y, even though B is fall down like this, falls like this, then Y is just 1. That's our expectation, right? But problem is that the critical path is different for this OR gate, right? Because so actually the B is connected to this AND gate and this AND gate. This is AND gate 1, this is AND gate 2, right? But you can find that on the AND gate 2. You can find the inverter. The inverter is here, so which means that the delay to this input of AND gate, and then the delay to this AND gate 2 is different, right? The delay is different because of inverter. It's inverter, right? So what will happen? So B false, the B change, the value of B changed from 1 to 0. So N2 will be change it like this, right? Because of this delay of AND gate. This is the TD of AND gate. Right. After some time, this N2 will be changing. But N1, this is N1. N1 will be changed after some delay, but this delay includes the TD of N plus TD inverter. Right? So it's slow. It can be slow, right? So this is actually this path until the N2, it includes the delay of inverter only, but for this node N1, it includes the delay of AND gate plus delay of inverter. So delay is equal. So if you see the waveform, you can find that the N2 is changed like this, then N1 change like this, but delay is equal. So Y, if we see observe the Y, and also we need to consider the delay of OR gate. We can observe that the Y signal change like this. Okay. So we can observe a glitch, right? So actually, if we do not consider delays of logic gate, then Y is the same. Y is 1, Y is still 1, even though B is changing. But because of different delays until the past Y, we can observe glitch like this. Okay? So this is our expectation, but because of glitch, the Y value becomes like this. Looks like this. Okay? So this is called a glitch, no? Circuit. Okay? So and then in order to avoid the glitch, then we can add some additional circuit. Okay? But this is not a critical issue actually. So we can run that we can observe glitch because of the different delays in the different paths. Okay. So we can remove glitch by adding redundant gate like this. So if we just add the additional AND gate here, we can remove glitch. But we don't need to. Actually, we don't need to remove glitch. Okay. So it is because until this time we are learning about the combinational logic, but after the midterm exam, we will learn about the synchronous logic. And then actually the synchronous logic is synchronized by clock signal. Okay. So actually it means that this intermediate changes, intermediate values are not important, synchronous logic. And then actually, so even though we learned about the combination logic, actually every digital system is implemented using synchronous logic. So every digital system uses clock signal. Okay. So if we use a synchronous logic, or if we use a clock signal, this intermediate changes, these like the glitches are not critical. Okay? Actually, these intermediate changes can be ignored. We can ignore intermediate changes. So actually, we don't need to consider about the glitches. Okay, we can observe glitches in a circuit because of different delays, but actually this is not critical. Okay, we cannot remove all glitches in a circuit. Okay, it's not possible actually. So you know the circuits are very complex. So it's not possible. Then actually glitches are not critical. Okay. So just to understand that we can observe glitches in the circuit. Okay, but you can also understand that the glitches are not critical. Okay. So this is the end of the chapter 2. Okay, so I will stop here and then any questions? Okay, okay. 어느 쪽 슬라이드?
엔드랑 오월에는 시간 측정 빼가지고 쉽게 빼가지고 타임 측정하는 네 거기에
여기요? 네.
그냥 쇼트 패스랑 문제 하나 연결되는 거 그냥 비교해서 측정할 수 있는 문제로 그런 게 연결해서
어떤 거요? 네.
목표가 많이 내일이 측정하고 싶은 거랑
네.
그냥 쇼트 패스를 기준으로
네.
엔드 연결한 거를 그걸 빼가지고 엔드 측정하고 5월 굳이 저렇게까지 두 개까지 추가로 연결할 정도로 복잡하게 해야
이거 하는 거예요? 복잡하게 계산한다는 그 딜레이라는 거는 우리가 이제 그 말했듯이 프로파게이션 딜레이, 맥시멈 딜레이랑 그다음 컨테미네이션 딜레이를 다 이게 메저를 해야 돼요. 다 디파인을 해야 돼요. 어느 우리가 이제 이 딜레이라는 게 타이밍 스페시피케이션이잖아요. 어떤 그 디지털 시스템에서는 이 두 개를 다 디파인을 해야 되는 거고요. 그래서 크리티컬 패스, 롱게스트 딜레이를 계산하려면 이거 해야 할 수밖에 없는 거죠. 네? Okay. So I start here. Then you look for your return. 감사합니다.